As we part, I'd like to congratulate you for sticking with this course throughout its 8 weeks. I hope that you have a good sense about networks. What I hope you got out of it is understanding what are the key properties of empirically observed networks, what are the processes that shape them that help us to understand what those empirical numbers mean, and what implications this has for various functions that the network is supposed to be carrying out. For example, whether it's enabling people to communicate or to search and find one another, or some of the cool and unusual applications where the nodes might be different products in a product space that different countries participate and compete in. At the same time, we've, in a sense, just scratched the surface of all of the wonderful research and learning that you can do in this area. One thing that I haven't covered at all are biological networks, and this is one of the largest application areas with many fascinating findings, ranging from understanding how different functions have evolved to how cells work to I mean, it just goes on and on. It's really, I mean, things like the relationship between genetics and disease. All of this now is heavily influenced by uh, our understanding of how things are networked together. Similarly, there's so many other application areas that we haven't, that you wouldn't even imagine. For example, network analysis of space that architects use to understand which spaces are going to be conducive to individuals flowing through, which spaces are going to allow them to communicate, just things of that sort. We also have not used some of the tools that are heavily used in some domains. So, for example, there's a most excellent book by Mark Newman, who's also faculty at the University of Michigan, called Introduction to Networks. And it's really a tome, it's a very thick book, where he shows you how using some heavy duty math and analytics, you can derive many network properties from knowledge of simple things such as the degree distribution. So you can actually derive what the size of the giant component will be given the degree distribution of the network, for example. It also looks a lot at different algorithms for detecting community structure and really grounds such approaches on, kind of in a statistical way where you're looking at ensembles of many different network instantiations and looking at whether what you observe is actually significantly different from what you would see at random. On the economic side of things, Matthew Jackson, who's faculty at Stanford, has written an excellent book, Social and Economic Networks. And things that we really didn't get into that much but that the book covers, are things like what strategically, how, if the nodes are self-interested in maximizing the utility that they get from the network, how will the network be wired? Or if you're playing certain games, I mean, we did the simple cascade model, but what if you were playing Prisoner's Dilemma on a network? How does the network topology affect the outcomes? Um, then Laszlo Barabashi and his collaborators are writing more chapters of the wonderful network science book, which is aimed more at a beginner audience. So I think you could probably understand, no matter your background, a great portion of that book. So other topics that we didn't get to this time around include how networks evolve over time. So Gephi actually has some functionality for visualizing how networks evolve. But questions that you might be interested in is Does the community structure change? Does the network densify? That is, does it become denser over time? You can track centrality. So, are there different nodes that emerge as being important during different time periods? So that's a whole area which it's sort of easy to extrapolate from where we are now to doing it over time. But I'm just sorry I didn't get a chance to do that with you this time around. Um, so another very fruitful part are these P star models, where you statistically determine factors that are affecting network formation. So rather than saying, "Oh, okay, it's going to have this probability of preferential attachment," you're going to actually run an analysis that's going to extract that from the observed data. Is the network growing preferentially or not? Is triadic closure a large factor in how this network has formed? And finally, cool and unusual applications, they're happening every day, all the time. Whether you want to understand what's happening in politics, in education, really, there's no limit to where you can apply network analysis. So I do hope you have found this class useful and that now you will go forth and apply social network analysis to whatever might interest you. So thanks for sticking with me through these weeks. Bye.